Okay, we're going to do a couple of application problems here just as extra practice with all these oscillator, energy, and force concepts. So for the spring oscillator, we'll take a horizontal spring. We're going to try to find the spring constant, saying that we know the amplitude and the maximum speed. So if I look at the spring oscillator, when it's over at the amplitude, it's not moving, and it's been stretched an amount equal to the amplitude. The maximum speed is when the spring is unstretched. So at the equilibrium point, for a vertical spring it would still be stretched, but the maximum speed would still occur at the equilibrium point. And at that point there's no stretch for the horizontal oscillator. So if we look at our system being the block and the spring, it's only interacting with the table and the earth other than that, but those two forces cancel out, so they can't do any work. So energy is indeed conserved. At the beginning it's not moving, so there's no kinetic energy, but there is a spring compressed, so I do have spring potential. At my endpoint, which is the middle, the equilibrium point, it is moving fast, but the spring is not compressed, and that's why it's moving so fast, because all that potential energy has been converted to kinetic. So we can look at our conservation of energy statement. We started out with spring potential, and we ended with kinetic, our maximum kinetic. So we're trying to find K. We know everything else here. So K is mv max squared over a squared, whatever that might be. If we wanted to, if we didn't have, instead of Vmax, if we had maybe frequency, we could say, or period, equivalent, we could use our frequency relationship, and we could just use our frequency relationship actually, if we know the F. And find our K. We could also use our time function. We know that Vmax is 2 pi f times the amplitude, so if we add the f, we could get this here and put it in there, and all of these would give us the same result. So they're going to, in some cases there are a lot of ways to get where we're going, just depending on the information we have. So for pendulum, we're going to try to find the length using the maximum speed and the maximum theta. So if I'm pulling it back, some angle theta max, string of length L. If this is the maximum angle, that means it's not moving there. And then I let it go, and it swings through that angle and has some velocity Vmax. If we know this and we know that, we're trying to find L. Again, energy is conserved. If I look at the pendulum bob, the thing on the end, and the earth, I don't even have to include the string, because the string is perpendicular to the motion, therefore it does no work here. It changes the direction of the pendulum bob as it moves, but it never speeds it up or slows it down. So if it's not doing any work, then it doesn't have any effect on whether energy is conserved or not. So all really we have is conversion between kinetic and gravitational potential back and forth. So my initial point, I don't have any kinetic because it's not moving, but I do have some gravitational potential. And then at the end, it's moving pretty fast, because if I say h equals 0 is at the bottom, then it has no gravitational potential. So the only question then is kind of how high was that? What is this h initial? If we use trig, this bit is L cosine theta max. This whole thing is L, so this little bit here is L minus L cosine theta max, or L times 1 minus cosine theta max. It's a useful little trick. We see that all the time. So to draw a good diagram, you'll be able to figure it out. So at the beginning we have that gravitational potential energy, mg times the height, which is L times 1 minus cosine theta max, equals at the end just the kinetic 1/2 mv max squared. So I'm solving for L, the m's go away, doesn't matter what the mass of my pendulum bob is. And I'll solve for L. So it's v max squared divided by 2 g times 1 minus cosine theta max. And that'll be my length. If I were to know something else, like maybe the frequency, then just the frequency alone is enough to tell me the length of the pendulum. That's the only thing that determines the frequency is the length of the pendulum. So knowing that would get me right there. I guess there's nothing really else I could know. I mean, if I knew like the net force or the acceleration at the beginning, that could help me out too, because I can look at the forces here. So just a couple of applications. Conservation of energy is really useful with these oscillators in terms of finding speeds, because we don't know, or we can't use Newton's second law in kinematics because the acceleration is not constant. So this is really useful conservation of energy.